Now we're going to take a look at how these vectors apply to things in the real world. And if you're in physics, this stuff is probably going to look really familiar to you. Very simple. I'll draw pictures and stuff as best I can. We have a ball thrown at an initial velocity of 70 feet per second at an angle of 40 degrees with the horizontal. So we have a horizontal, and we're going 40 degrees. So here's our 40 degrees. And it's 70 feet per second. So we'll label that on the vector itself. And we have, of course, a vertical and a horizontal component. So I'll say this is A and this is B from our AI plus BJ. So now we need to find out what those measurements are. Well, you can look at it from a right triangle standpoint. That will always see you through. Since we're dealing with a horizontal and vertical, they're going to be perpendicular to each other, which means we're dealing with a right triangle. But we can also look at it in terms of vectors. Remember that we can write the vector as the magnitude of v times the cosine of theta for the first component, and the second component is the magnitude times the sine of the angle. And this is really handy because that's exactly what we have. This 70 is the magnitude of the vector, and our theta is 40 degrees. So we have everything that we need, we just need to plug it in. And this will be our A, and this will be our B. So we have magnitude, of course, 70, so this is 70 cosine of 40, and this is 70 times the sine of 40 degrees. Make sure you're on degree mode, and we should get that this is 53.6 comma 45, which means that the horizontal component is 53.6 feet and the vertical component is 45. And that's pretty much all there is to that. Right, now let's take a look at an airplane, and this kind of goes back to adding vectors together. So let's see. We have an airplane velocity with respect to the air is 580 miles per hour. It has a bearing of 300 degrees. Now this bearing thing is going back to 0 degrees being north and going clockwise around. And then there's wind that's acting on it at the same altitude of the plane. It's from the southwest. It has a velocity of 60 miles per hour. So I'm going to first of all draw in coordinate grid here so we can make sense of where all this is. So if the plane is going 300 degrees, that's its bearing, that means that it is over here. This bearing is 300 because this is 270 in terms of bearings. This is going to get a little confusing with the different directions, but this is the way it's going. And it's going 580 miles per hour. So that's the magnitude of our vector. So this is 580 miles per hour. And now the wind. The wind is from the southwest. So if it is from the southwest, that means it's pushing something towards the northeast. So it's pushing towards the northeast. Well, that doesn't make much sense to have it there, but I'm going to take this little vector that I have, and I'm going to add it onto, it's having an effect on the final destination of that plane. So by the time the plane sets its direction, its course of direction, and if it doesn't adjust for the wind, it's actually going to end up where that blue vector is. So we need to start looking at some angle measures here and figuring out exactly what's going on. One thing for this green vector, which was the airplane initially, is it's only 30 degrees off of the axis, which means that this angle here is 150 degrees. So now we're going back, shifting back into that normal mode where this is 0, this is 180, and so on. So if we have a vector for the airplane, then we will use that component form that we used before. So it's the magnitude, which is 580, times the cosine of 150 degrees. That's where it's headed. Then we have 580 times the sine of 150 degrees. Okay, now let's talk about the wind. Now when we had this back down here, it was headed northeast. That means it's exactly in the middle at 45 degrees. And its magnitude is 60 because it's going 60 miles per hour. So now we have the wind, and that's 60 times the cosine of 45 degrees, followed by 60 times the sine of 45 degrees. Now, if I add these guys together, because the wind is having an effect on the plane, I'm just going to write it out as plane plus wind. So we have a new vector. So I'm going to add these guys together. And when I add that together, make sure you're in degree mode. I have negative 459.9. And when I add these guys together, I end up with 332.4. So there's my vector for my final spot for my plane. So that means that this part right here is negative 459.9, and the vertical component for the blue one is 332.4. So that's where it will actually end up if it doesn't adjust for the wind. Now, what is the true direction and what is the speed with respect to the ground? Well, the speed with respect to the ground is the magnitude. So we're dealing with only the blue vector now. So speed is the magnitude. And to do magnitude, of course, we're going to take square root of negative 459.9 squared plus 332.4 squared. And that will get us to about 567.4 miles per hour, which means that it seems like it's going a little bit slower to us on the ground than it actually is. It was actually going 580. So it's being slowed down by the wind a little bit. And then what is the actual angle that this is traveling? So we want to know, what's this? What is our theta out there for our resulting vector? Well, we know that the tangent of theta is b over a. That is, for us, 332.4 over negative 459.9. Remembering that we are indeed in the second quadrant, and tangent's only good for first and fourth, we're going to have to do some adjusting, but I'm going to do my inverse tangent of 332.4 divided by negative 459.9, and that's going to tell me that we have negative 35.9 degrees. That's what it says, but that's not where we are. In fact, negative 35 degrees would be down in this direction. Again, we're going to add 180 to get our final. So adding 180 degrees, we are really at 144.1 degrees. And that is the end of section 6.1.